All right, everybody. Welcome for my talk. I am Luigi Cruz. I work at the SETI Institute. That stands for Search for Extraterrestrial Intelligence. It's based on California, and we have a bunch of telescopes and a bunch of radios, so that's interesting. So my talk today here for you guys is the Allen Telescope Array. It's a telescope on Northern California. We have 42 antennas, and we do lots of experimental work at this location. So it's basically, you can think of the telescope as a very, very large SDR processing radio stuff from the sky. And this photo is the recent park fire, so everything was orange, quite like Blade Runner, so interesting. So without orange, this is the Allen Telescope Array. Each of these dishes rotate, and it's on a very rural area, like 1 hour from any city, very, very secluded because of radio waves. We don't want to get the interference from FM stations, the LTE towers, and others. So we chose to be between a valley with all mountains surrounding the area. We have the Mount Lassen, that is a national park. I also have Mount Shasta, and we sit right in the valley. So the RF environment on this location is very, it's better than elsewhere, but we still have satellites downlinks like Starlink and others. So we have to keep in mind of that. And the Allen Telescope Array was mainly built because of aliens. So at the time it was built around 2007, there was no purpose-built telescope to look for technical signatures from other planets. So they chose to build the ATA at this location for a specific purpose, and this purpose was to be good at finding narrow band signals being transmitted from other galaxies. As many of you have watched this movie called Contact, we are not actually, in fact, using a headset to search for weird noises in the data received by the telescope. We use fairly more significant processing power than this. But let's get started by looking at the history of the telescope. So first of all, it was built between 2002 and 2007, as I mentioned, for search for extraterrestrial intelligence. And it's called Allen Telescope Array because a large chunk of the original funding was donated by Paul Allen from Microsoft, and recently from other benefactors like Franklin Antonio, from a co-founder from Qualcomm. We were able to upgrade the dishes to something cryogenically cooled and much more cool than the original ones. So as you can kind of see in this photo, we have 42 different elements. So that's one array, and each dish has 6.2 meters in diameter. And it can swivel 360 and also up and down and in elevation. Each one of those dishes produce around 1.5 gigahertz of data for each polarization, and each polarization has each polarization is 1.5, and two polarizations is 3 gigahertz of data. So it's quite a lot of data when you think about 42 antennas producing 3 gigahertz each. So that equates to around 60 gigahertz. We have around 28 antennas at the moment operational with the new feeds, and each of these antennas transmits to a central location. And that equates right now for 1.5 terabits per second of data that needs to be processed in real time. So we can store 1.5 terabits on disk and later process it. So we need to do the beamforming, all the data analysis online on 1.5 line rate. And that's 8-bit samples, so quite a lot of dynamic range there for radio telescopes. It's 8 bits comparable to RTL SDR, if you are familiar with that. And also, we have a wide spectrum receiving bandwidth. So that goes from 900 megahertz And actually, it goes actually lower, like 200 and up, until 12 gigahertz. So that's a lot of data and like almost 12 gigahertz of bandwidth, much more differently than other telescopes around the world that can get to higher frequencies, but really a tiny speck of that frequency, like 20 megahertz or 1 gigahertz. So we have the advantage of being able to tune from FM to upper X band on the telescope. So this is a video of the telescope moving. It's tracking a low Earth orbit satellite passing overhead, and it can keep up with the tracking. The speed of the antenna can keep up with the satellite quite well. Don't mind the other dish there. It's doing other things. It's kind of wobbly. Each antenna moves 360, as I mentioned. You can see a silver pipe there. That pipe is meant to throw cold air into the element, the receiving element for cooling on the summer. It can get to like 45, 46 Celsius at the site. So we have to have good cooling, otherwise we will be out of the sky and not getting data. And this whole assembly moves in the azimuth and also in elevation. So that thing arm there will do the elevation, and the other thing will rotate to do the azimuth. So if you zoom in into the antenna itself, you have this component. This houses the receiving units of the array. And we have a RF transparent cover to cover the elements from the sun, and also shield some of the RFI out of the receiving end. And here it's a better picture of the receiving end. It looks like a very expensive Christmas tree. And it's locked periodic, so each element, the width of each element will be geared at receiving a certain frequency. So that's why we have from very tiny ones for the high frequency waves, and then the bigger ones, the larger ones for the lower frequency. And lower frequency, I mean 200 until 12 gigahertz. And this feed is also cryogenically cooled, so it gets almost to absolute zero on the antenna, the Christmas tree part. And to maintain this temperature on the 45-degree heat from the middle of California, you have to have an enclosure that pulls a very, very fine vacuum, so the temperature doesn't get conducted to the element itself. So in this assembly, we have, better shot of the width. It's all gold-plated copper. And connected over SMAs on the top on the base of the Christmas tree. So here you can see the controller of the board, all the electronics controlling the turbo pump. The turbo pump is the assembly there on the lower right part with a red stripe. And then we have the cryocooler that will cool the antenna to minus 270 Celsius. And also the vacuum pump on the way back with a red stripe there. And they work 24/7, and after thermal equilibrium is reached, it just uses 100 watts to keep at 270 Celsius at the operational temperature. So I mentioned this is a blueprint of the telescope. We have 42 antennas installed. And it all links to a central location at the center of the image. That is our offices / data center. You can see there the cooling systems. We need to have a lot of cooling to make this work. And we also have Starlink receiving, because we are in the middle of the woods, and if our fiber, we have 2 gigabits Ethernet, fiber internet. But if that fails, we also have a failover over a Starlink up there. So this is our data center. So in the left part here, we have the RF chain. This is where the signals from the antennas will arrive and get distributed to the digital end. So So this is the RFCB. So it will, so when the signal reaches the antenna, it's converted to copper, and then the copper will be amplified and filtered. And later it will be converted to fiber optics. So the RF signal represented over fiber to our central location, that is the server. And this board right here will be responsible to get the incoming signal from fiber and then convert it to electric signal from copper, and then do some further amplification, filtering, and also passing to the next stage of the processing chain. So this is one of those boards laid out on the table. You can see lots of passive elements here and also some LNAs. So in the edge of the board, you can see the fiber connectors. Then it goes to the fiber to copper converter, and then to some LO, because all the frequencies are, for example, 15 gigahertz, and it needs to be mixed down to something that the IF can receive, like 1.5 gigahertz. So it's all the LOs from our rubidium standard comes in on this board. It's get mixed with the copper signal from antennas, and then the output is sent back to the other amplifiers. This is a closer shot of the fiber to copper converters. So the fiber gets in there on this transceiver here. Then the optical signal gets converted to copper, and it gets filtered on this passive components and split into 4 channels, so we can tap it for other reasons, but we are currently using 2 of them. And here is the ATA amplifier module. So after the signals from copper are brought down to IF frequency, it's passed to this module that will do further amplification of the signal, filtering of the signal, because we have lots of bandwidth here, so they all did that. And later, after the signal is ready, it was amplified, filtered, and down to the IF, we will use our very expensive FPGA boards to do the digitalization of the signal. So the signal is analog on the receiving end, so that's 1.5 gigahertz per channel, and then we need to use this FPGA that has an ADC integrated with it. So instead of having the FPGA on one end and ADC on the other one that will take the analog data to digital format, this Xilinx part have the FPGA, the ADC and the FPGA integrated within a one package, and that will make our lives much more easier to deal with. So 4 antennas, each antenna 3 gigahertz. We have each of these boards processes 12 gigahertz of IF frequency. In comparison with like RTL SDR, you can do 2 megahertz. So a few orders of magnitude more data than the RTL SDR, and it's all connected over 100 gig networking. So you have 2 connections, 100 gig each, connect to our back switch that has 100 gig and goes to the computers. We are interested on upgrading the telescope to a direct sampling operation. So instead of down converting a high frequency to IF and then digitizing, we want to digitize all the RF frequency that the telescope produces. So instead of 1.5 gigahertz, we are looking to convert the whole 12 gigahertz of each antenna for each polarization. So this part here, the FPGA, will need to be upgraded to something more expensive, but that has to be able to sample at 24 gigasamples per second, and for each channel, and overall around 48 gigasamples per second to produce 24 gigahertz for each board. So we are looking for another vendors, Mercury or Chariot from 64 gigasamples ADCs to integrate with telescope. And once we get those working, we will need one of those for each antenna. So each of the 42 antennas will ultimately produce 24 gigahertz each. So that's around 1 order of magnitude more data to process when we upgrade to another direct sampling. But we will have also 1 order of magnitude more bandwidth to process and get more science from it. Yeah. Oh yeah, and all of these are synchronized on the sampling with central location. So all the RF SOX boards that we use are coherent with each other, so we can correlate the signals and produce some other some science observations with it. After everything is being converted back to digital, we need to process all of this data. So as I mentioned before, is 1.5 gigahertz of data for each polarization of each antenna, and 3 gigahertz per antenna. And we have 28 antennas, so that will produce 1.5 terabits. And we have, at the moment, 8 servers. Each server has 2 GPUs instances working, so 1 GPU and 1 network interface, 100 gig network interface. And each one of those is receiving 91 gigabits per second to process in real time over the GPU. So the GPU needs to process a lot of data to be able to keep up with the data. Oh yeah, we use a Mellanox Connect X5 card, so that's dual 100 gig ports, so that we connect directly to the switch that is connected to the RF SOC boards. Another upgrade that we are looking at the future is to increase the density of those servers. So instead of using 2 instances of GPUs, we are looking to use 4 instances per server, 4 use servers. So we will have like RTX A6000 or RTX 6000 ATA NVIDIA cards paired with a 200 gigabit internet card. And that will process twice the amount of data per instance, and also twice the amount of data per server for use server. So that will be an upgrade to what we have now with that direct sampling coming online. This is all the servers that we have. They are mainly Supermicro ones. And after the switch, we kind of don't care about the vendor. The whole telescope was built to work with off-the-shelf components since from the beginning. So even the antennas components are available on GGKey if you want to buy it. If you want to build another ATA, you can with off-the-shelf parts. So the same thing applies with the data center. So we have servers from Supermicro. They are normal servers. We have the GPUs, normal GPUs, gaming GPUs. We used to use RTX 3090s to process this, so high-end gaming card, and also enterprise 100 gig Mellanox cards for the connections. So it's more like a close-up. So you can see the A5000 GPU paired with one of the Mellanox cards. That is the purple cable going into the GPU and being processed there. Oh yeah, so each server has an NVMe card. So instead, we can't keep one single NVMe SSD can't keep up with the data rate after the beamforming. So we'll need to use like a PCIe 5 carrier board by 16 and split that with 8 NVMEs to get something close to the data rate that we need to write. So that's around 32 gigabytes per second of data that each node will receive and store on the NVMEs. And after the observation is done, the NVMEs needs to be ready to the next observation, So all the data needs to be transferred to our JBOD system. And currently our JBOD system is composed of 3 different servers. And the entire thing has around 3 petabytes of data on site, or on location, to store all the observations, science observations. A question that I often get is that why don't we ship the data out to be processed elsewhere instead of the middle of a rural area in California? And the reason is it would be very slow to do it over our fiber internet. Even if we've upgraded to something like 10 gigabits internet, that's a fraction of the total data generated by the telescope. So that wouldn't work. So instead, we generate 1.5 terabits. We have 10 gigabit internet. Terabits, gigabits, doesn't work. So we need to process and store on network. And also would be, even if we could, would be very, very expensive to do that because of ingress and egress fees. So we do all in-house at the location. And by the way, all of this is open for visitors. So if you're around Reading area and you want to visit the Allen Telescope Array, you can totally do that. You can do like by your own, but just let me know, and I will probably be there so I can give you a guided tour. So in retrospect, so we have the antennas on one side here, getting the signal, or the good signals. And then it needs to be transmitted over fiber to our data center on site. It gets to the analog cluster. The analog cluster will convert the fiber, Ethernet, optical data back to copper. Copper will be filtered and then passed, digitized with our Xilinx FPGA RF sock board, and then transmitted over 100 gig Ethernet, gigabit Ethernet to our processing clusters. And that's where our code run. I work mainly on the GPU compute processing area of the telescope. So each server has 2 AMD CPUs, 2 A5000 class GPUs, 2 ConnectX 100 gig, and 2 8 terabyte NVMe cache. That 8 terabytes is 8 1 terabyte drives. So quite a lot of data to get. And our in-house processing system is called BLADE. It's called like Breakthrough Listen Accelerated DSP Engine. It's a insane acronym, but it do beamforming. So for you guys for people who don't know what beamforming is when you have a bunch of receiving elements, like we do at the Allen Telescope Array. We need to synchronize when the signal is received by each antenna, because they are distributed over a large area, like a 350 meters baseline, so that the distance between the farthest farthest antennas. So, and like the signals travel at the speed of light, that's around 30 centimeters every 1 nanosecond. So they will need to be that difference needs to be accounted in software after we receive the antenna, the signal, before we sum the signals to do some science. And that's why we need big GPUs and processing real time, because instead of, we will receive 28 antennas, and that's the bandwidth times the number of antennas. And after the beamforming, after we point directly at the signal that we want to receive, that gets converted to a single antenna, a single virtual antenna that is the summation of all the receiving antennas, minus very small inefficiencies of the array. But basically, what beamforming does is to concatenate all the data of all the antennas, so you get more amplitude. So if you are observing like another galaxy or like Mars, you can do the beamforming and get a much stronger signal by pulling the antennas together. So that's where BLADE comes in. It needs to process like 1.5 terabits per second of data, and needs to be processed very quickly. Like each instance right now receives like 90 gigabits per second. And that needs to be received on the network card, sent back to the CPU currently, and then sent back to the GPU for processing. After the GPU is done processing, it needs to send to the CPU, and then the NVMe for persistent storage. So our DSP part is BLADE, created on site, but used in a lot of places right now. And other observatories that we run, like the GBT, the Green Bank Telescope in West Virginia, and also the VLA, our cosmic programs at there. So BLADE is, so each component of BLADE is called a module, kind of like GNU Radio, but on steroids. So the data receives in like integer 8, so that's a way to represent your digital signal, and then it is to be transcoded, casted from integer to float 32. So that's what the first module does, a cast module. Everyone is familiar with that. And then we need to channelize, and channelize is basically converting from the time domain to the frequency domain to be processed more efficiently. So instead of very sequential data in a single time domain, we do the channelization, and that creates a bunch of channels, and each channel has its own time domain. So it's basically doing an FFT, and then looking at the waterfall. So each waterfall line is represented of a channel at what we do here, and we can process each channel independently from the channel from the other side on the other side. So we can parallelize the data processing much quicker, much faster this way. And after the data is channelized, we can do the beamforming. So that's basically getting the phasors. With phasors, we have a lot of math, because you need to get the locations of each antenna in relation to the surface of the Earth. And then you need to model the surface of the Earth to the target at other galaxy, and then account for the rotation of the Earth, and also any movement of your target. So all the phasors, this coefficient for the beamforming is called the phasors, and the phasors will change every around 16 milliseconds. So we need to do all those calculations for the phasors in real time and pass to the beamformer. And the beamformer will do is basically multiply the complex float 32, that is the data, with the phasors, and then it will concatenate every synchronized antenna into a single accumulator to later to be passed to another module. That is polarization. We receive horizontal and also vertical polarizations, but there is also a right-hand circularly polarized and left-hand circularly polarized that some antennas will transmit with. That we also can generate with proper calibration. And then the detector is basically doing the log power and also doing some cross-correlation between the polarizations. And then casting again for passing to the CPU, because float 16 is often is half of the bandwidth to be passed to the CPU instead of float 32. So we sometimes cast. And also many more modules, like the correlator. Instead of doing the beamforming, you do all the correlation between all the antennas. You can kind of generate an image of what we are observing. So for example, you point your telescope to a nebula. It's like a cloud of methane, for example, and the methane will resonate in a certain, very specific frequency, and you can receive these frequencies. And with the correlator module, you can paint like a 2D image of that nebula with a radio telescope. So radio is, you can generate images from a radio data with the correlator. And also others like QP files for storing the files. And I won't go too deep into how BLADE works here for the sake of your time, but it's basically a very efficient way to do lots of processing in real time. So if you do, if you dispatch naively your work to the CPU, you need to your GPU, you need to transfer data, wait for that data to be transferred, and then run the computation. But BLADE behind the scenes will do this in a slightly different way, and that way is to transfer the first data, start to compute the last data, and do this chaining. So there's a transfer going on while there's a compute going on. So you're utilizing the transfer engines of your GPU and also your compute engines of the GPU in 100% instead of waiting for the transfer to be ready to start processing. You can transfer we can transfer, and while it's transferring, the previous data can be computed. So you get the 100%. So, and this is one of the other things that BLADE do behind the scenes. It's written in C++, and all the DSP modules are written in CUDA. You can go to the repo that's in the end of the slides and take a look at the kernels, the CUDA kernels that you use for the Beamformer correlator. It's all open source, it's MIT licensed. So if you have a telescope at home, you can use our code. You can also contribute with BLADE if you want to. And as you can imagine, the transferring data to the CPU, every place it needs to be like network card, CPU, GPU, then GPU, CPU, NVMe. That will create some latency between the components data shuffling. So we are working on a next generation pipeline for the Allen Telescope Array that will eliminate all the CPU copying parts of the pipeline. So the data will be transferred directly with like RDMA, like remote direct memory RDMA. GPU Direct is a GPU NVIDIA name for the technology that will basically copy the data. The UDP packets being received by the network card is copied directly to the GPU memory without passing over the CPU. And also, we eliminated some post-processing factors like the channelization for certain science data that we need to build. So we are basically doing an FFT of the size of 3 million bins over 28 antennas, if you want to. So your like GQRX with your gain radio will create at least like around 300,000, but we do this 1.5 million times every second with all our GPUs. This is what I mentioned about eliminating also the NVMe from, if we eliminate the post-processing step and we do everything in real time, we don't need to store things at the NVMe and then read it. So that eliminates around 3.6 gigabytes of read-write from the NVMEs instead of just doing everything in sequence without writing to disk. We are working with NVIDIA, NVIDIA's engineers and managers to apply the NVIDIA Holoscan, that is a SDK meant for parallel GPU processing into the telescope. And it has, as I mentioned, modules. So each module is responsible for something. One of them, the most interesting one, is the Advanced Network Operator. That is a module that can take the UDP packets being received on the GPU, strip out the header struct, so that the header will tell you the timestamp of that packet and also where it came from, the antenna and the channel. That will be transferred to the CPU for memory management, and the rest of the payload will be transmitted directly to the GPU using RDMA. And that will save a lot of processing time and CPU time, because all the data is being sent directly to the target where it's being processed or stored. So that's why we are using the NVIDIA Holoscan. That is part of the next generation pipeline of the ATA. And we are currently on stages that is kind of working. So here you can see my other project called CyberEther. That is a GPU-accelerated data visualization program that runs on iPhones, iPads, browsers, laptops, Windows laptops, Android, Windows, Mac, whatever. It supports Vulkan, Metal, Web GPU. It works everywhere, basically. And you can pass like signals to it, kind of like GQRX, but everything is GPU accelerated. So you can plot it much faster. And some visualizations are kind of cool. So that's why I used it. So I was using Holoscan to receive the UDP packets. The UDP packets were being sorted to be a DSP component. So that's a larger data set of all the antennas synchronized with each other, and then passing the pointer to that data to CyberEther that is running on the CPU, that is running on the GPU, and that GPU is the same GPU that is receiving the data. So there's no copy between Holoscan and CyberEther. CyberEther will take the input data, run the FFT, run the range, the amplitude finder, and display and draw the frame buffer. That frame buffer is also on the GPU, and that frame buffer, instead of going to a display, it can be encoded with NVIDIA NVENC, that is a H.264 encoder, and send over the internet to whatever you are. For example, when I did this, I was working from Brazil. So the server at the ATA was receiving the data, sorting the data, send the data to BLADE. BLADE was doing the beamforming. Then the beamforming data was sent to CyberEther within Holoscan, and CyberEther was rendering the screen that we are looking at and encoding it directly, encoding the frame buffer from Vulkan with NVENC instead of and sending me over UDP and VPN over my home, where my local CyberEther client was receiving this data and rendering it on the screen. So instead of passing 90 gigabits per second over the internet for my machine to look at the data, I can do this with Holoscan, BLADE, and CyberEther on a server. Instead of passing gigabits of data, I pass 5 megabits of data that is similar to a YouTube video playing, and you can do all the interactions with mouse and keyboard, and the quality is actually full HD at 60 FPS. So you don't take a hit on FPS and quality like you do in VNCs. And it's all to CyberEther and all the non-memory copying things that we do. So very efficient, and we can see, in this case, 90 megahertz of data of all the antennas being formed together on a single node, 12,000 kilometers away from the data, the place it's being converted. This is 4 of them, so that here is like 400 megahertz of data in a single node. Same video data, around 5 megabits being transmitted. And also, since we have a telescope and the telescope can track Mars, we just pointed the telescope to Mars and saw what happened. And what happened was that we saw these 2 peaks here. So the first one close to the DC. DC is just a normal thing. That's not a signal, actual signal. You have 2 signals. One of them was Mars Odyssey that was orbiting Mars at that time. So that's the peak. It's like it's the X-band transmitter of the spacecraft transmitting telemetry data back to the DSN. And we were able to get this data, process over Holoscan, BLADE, and also CyberEther to visualize this data. We can decode it right now because the SNR is not too great, but we can see the carrier of the phase modulation being transmitted in Mars. And the other pick is actually Tianwen, also a Chinese counterpart of their orbiter. I think there's also a lander, but I'm not sure. Also, signal, X-band, same thing, Mars, very far away. So yeah, we were able to make everything work. So every single component of this chain had to be excruciatingly made on purpose to be this to make this possible. We are receiving the data, processing the data, beamforming, and then rendering, and then transmitting to the client. Also, another space demonstration is the GOES satellite. That's the geostationary observation station from NOAA. It's a weather satellite. It's pointing towards Earth at the same location 24/7, and it's taking pictures every 10 minutes. It's transmitting another picture. You have 3 signals here. One is the middle one is the DCPR. That is, all the ground stations in remote areas will transmit some signal to the telescope, and the telescope is just relaying the data back to NOAA. So NOAA can gather all the data it needs from remote locations with the satellite relay service from GOES. The other tiny signal, pointy tiny signal on the edge there is the telemetry and control signal. That's where NOAA receives the status of the satellite and also the sensor readings, etc. The tiny, the wider signal in the middle of the CPR and the telemetry is the H-RIT signal. That's around 1 megahertz of signal. And that is actually very easy to receive. If you buy on Amazon like $100 kit with a Wi-Fi antenna, grid antenna converted to work on the 1.9 megahertz, 1.9 gigahertz, you can point that to anywhere in America. You can point that to the telescope and receive the images being generated by the telescope yourself without internet and whatever. So that's a fun project to try when you have time. Just point at a satellite and receive weather data on your lawn. And the Chunga signal right there is like a DVBS2 signal. It's not actually raw data. It's compressed raw data. So the satellite will send to the NOAA headquarters. There's a bunker somewhere in the East Coast. That bunker will get all the actual raw data that is transmitted on like X-band. That has like 20 megahertz wide. And it's processing, sending back to the telescope. And the telescope is distributing that processed raw data, the kind of raw data, compressed raw data, back to the clients. And you can use a DVBS2 receiver to receive the data. That's much higher resolution. That's around 500 meters per pixel on the red channel. So you have the whole globe, like 33% of the Earth, with 1 kilometer per pixel resolution. So that's quite cool, but you can do that on the SDR because it uses some complicated convolutional codes to do the error detection. So you'll need a DVBS2 card. It's a PCIe card that you can hook up with your computer. And also, another peculiarity of the signal is that it transmits in dual polarization. So it's actually 2 signals interposed by each other on the same frequency. But you can separate both signals by separating the right hand circularly polarized signal and the left hand. So if you have a septum, you can separate 2 signals, and you basically get twice the bandwidth on the price of 1 bandwidth. That's a trick that NOAA used to double the data rate from this thing without having to ask FCC for more bandwidth. So it's kind of cool. I have other talks about this telescope online if you want to know more. My friend Lucas Teskey also, we gave a presentation before. So that's the GO16 being received by the Allen Telescope Array. Also, non-space demonstrations. So there's a city around, very tiny city around half an hour from the telescope. We pointed the telescope to that city, and we could see our Wi-Fi and the thing getting saturated to oblivion for LTE signals. So that's the downlink LTE signals being received on the antenna. So we basically pointed 42 antennas to the one city, beamformed the data together, and received LTE from the antenna. We have actually a project to receive LTE from space, but they need to send a rover to the moon, and then we can receive the LTE from the moon with the telescope. We actually do data. We actually do science instead of farting around with the telescope. So the image that I mentioned, the blob of cloud of the correlator is there, like a image. There's the intensity of the density of the composition of the cloud, for example, all being received by the telescope and all the papers that we published. In the future, we want to run multiple things at the same time with the help of Holoscan. So we want to run the correlator, we want to do the beamforming simultaneously, and also do neural network inference in real time. So get the data and run a model, like a CNN model, and then get the output of this module. And if it detects something interesting, we can save the data that the model looked through for a human to look at. And we are hoping like 100 plots a day that can be sorted by the scientist and looking for fast radio bursts and other scientific discoveries. Other than this, we also are in Green Bank Observatory. We have a subsystem there looking for narrowband signals being transmitted. This is the antenna they have there. Instead of an interferometer, it's a very, very, very large array. It's West Virginia, so I put a cat there with a cowboy hat. And this is just definitely not into scale because there's nothing on their side. But, oh yeah. Yeah, so it's very tall, as you can see. It's taller than the Statue of Liberty. And yeah. And this is on top there, like the tiny pointy thingy on top of there. This is where you can access it. So people can get into the feed of the thing. And each feed has like a blower to melt snow because snow will interfere with the reception of certain frequencies. So all these elements needs to be clean of snow. That's why the blowers and also the infrared blaster there. And each of those are meant for a different frequency. So that's the diameter varies between them. Comparison? Oh yeah, another fun fact. They put microwaves inside cages there. Yeah, so I was like, I'm not sure if that helps too much. And then I got my phone with CyberEther on my phone and pulled up STR. Someone turned on the microwave, and I could see the microwave the signals at 2.4 gigahertz just popping around when the microwave was running and the cage was closed. There's some theories that the signal can escape through the power cord, and the power cord acts like a big antenna, and you can see all the signals being blasted out of the microwave. Also, we are in the VLA. We have a subsystem in the VLA processing the data there. It's running BLADE on the GPUs. Also, yeah, so I think 2022 or 2023, we had a brilliant idea to cool the servers using mineral oil. And we went to Houston at Doug, a company that makes these tanks. And this tank's basically a car radiator immersed in mineral oil with the computers dipped in the mineral oil also. So what they do is to strip the fans of the computers and dip into the mineral oil. The oil is getting heated by the component. It convects to the top, gets circulated on the radiator, and the heat gets exhausted over a chiller outside. That was Houston, so I believe them it works. So no actual like AC, no heat pumps involved, just a chiller outside, and that runs passively over the mineral oil. It's something that we can we want to look at in the future. And also, they can't use fiber optics because the oil will get into the fiber optical interface and mess up with the power levels. So they use copper to the last mile. So there's a switch, in between the tanks, and then fiber gets in, gets converted to copper, and gets to the computer. That's it for me today. If you want to download Blade or see my GitHub, lots of things there, just go to my Luigi F. Cruz, github.com. Or if you want to contact me, I have a bunch of contact places at luigi.ltd/contact. And I am happy to answer questions if you yell at me very hard. Yeah, the question was, are there plans to expand the Allen array? And so, yeah, that's a good question. So the original idea was to get 350 elements, but then it got to 30, 32, and then the Navy donated us 10 more antennas. So that's the 42 antennas. But currently, there are not. We are currently refurbishing the ones that we currently have to have the newer feed and etc. But after that's done, who knows? I think we can still have the ability to produce more antennas if we need to.